last time we started discussing this idea of doing a hypothesis test for the general linear hypothesis. And so the idea was that we had this, it comes up, yeah. So we have this hypothesis that puts constraints on beta, right? So you have a bunch of linear constraints on the coefficients of the linear model, and you can write it as A beta equal to 0, like that, where the rows of A are linearly independent. So A has full row rank. Alternatively, you can write it usually in our case as Z gamma, where Z is a matrix. Gamma is now a set of free parameters. So these are dual representations. The first one is saying beta is in the kernel of A. The second one is saying beta is in the image of Z. And so how to get from the first representation to the second is like a linear algebra problem. In most examples that we do, this is sort of quite obvious. You can produce something like that. For example, this example that we did, you said beta 0 equal to 0, and then beta 1 equal to beta 2. You can define one of them to be gamma. The other one would be like, for example, beta 2. If it's beta 2, then beta 1 would be 2 gamma. And so your Z would be determined once you plug it into basically X beta. You could see that I can represent, let's see. Okay, so this Z is not, it's bad notation. So there is something wrong in this slide. So anyone? So if I write beta as Z gamma, then this is not going to be Z. Yes.
That's a vector, right? Z has to be a matrix.
Z has to be a matrix, but if gamma is one-dimensional, so let's say in this case, in general, it would be like D minus Q by 1, where Q is the number of constraints, D is the dimension of beta. So beta has 3 variables. We have 2 constraints, so D is 3, Q is 2, so I get 1. So gamma is one-dimensional, so this Z would be D by 1. Okay, so that's not the problem. The problem is that I introduced this notation later. So I wrote this, I called something Z. Later we moved on, I redefined Z. So if I write beta as Z gamma, so what would that Z be in this case? So if I write things like this, so suppose I have the constraints, I want to write beta as Z gamma, and I called beta 2 gamma, so what would Z be? So if I want to write something like that. Beta 0, beta 1, beta 2. Times gamma. Yes. Sorry? Zoom in. Is that good enough? What is beta 0? 0. What is beta 1? 2 gamma. What is beta 2? Gamma. So that would be our Z. Then what this would be? So I'm plugging that beta into X. So this is Y equal X beta plus epsilon. I'm plugging that beta in. This would be X times Z. Okay, so this is the new design matrix. I called this Z originally, but later we changed notation. So when you plug beta equal X like Z gamma, then XZ would be your new design matrix. And it turns out, so this is going to be, in this case, it would be N by, in general, it would be N by D, and this is D by d minus q. So this thing is going to be n by d minus q, which is correct. So this is going to be a vector. 2x1 plus x2. So you just sum some of the elements of the columns of x. Okay, so in the new notation, this would be, I'm going to call this maybe x tilde. So this would be x tilde. This would be x tilde, x tilde, tilde, x tilde. And then you can fix the rest yourself. Okay, so this is with the new notation. So once you plug this in, you get the reduced model. The reduced model has one free parameter. Yes.
Do you have to do it with Z or can you do it with A from above?
So how do you do it with A?
So,
I want to enforce those constraints, right?
so then you have to plug in the beta values and then if you do.
You don't have to. So you can try to solve this problem with those constraints. So you have to do at least the squares. So alternatively, solve, minimize y minus x beta, original model, beta in RD, and a beta equal to 0. So this is a constraint optimization problem. So you have to enforce these constraints, and you can numerically solve this. There are optimization techniques that allows you to solve this like a constraint optimization problem, sometimes called QP, quadratic program. Okay. So these are nice problems in optimization. Okay, so you could solve this with linear constraints or linear inequalities. Like this is linear equality constraints or linear inequality constraints. So for example, you can constrain beta to be between in a certain range. And there are techniques for doing this. This particular type of problem is simple because I can rewrite this like z gamma and then plug in, I get unconstrained least squares, which we know how to solve, at least on paper. Even if you know the actual closed form formula, you're not going to necessarily want to try to solve this using the formula. In like numerically, if you want to solve this or even the unconstrained version, there might be better ways of doing it. At least you don't have to like invert the entire matrix. You just have to solve a linear system equations. That's for a different like class. How to actually do like solve this. In practice, you don't invert the matrix. You just need like to solve the linear system at least, like x transpose x on this side, and then on the other side is x transpose y. And this matrix has a particular form. It's like a positive definite matrix, and it's already factorized. So you do a lot of interesting things. In any case, did that answer your question? I suppose it answered the question. Yes. Okay, so you plug in, you get the reduced model, you solve this. Solve means like I do least the squares, estimate of the parameters, I get the SSE. The SSE of the reduced model is just the usual SSE in regression. And then I have the full model, I can fit the full model, compute beta hat using the OLS, I get an SSE. SSE is a measure of how much unexplained variation remains. And then so I compare these two. Because the reduced model is nested within the full model, the SSE of the reduced model is greater than or equal to the SSE of the, so this one is going to be bigger than this one. And we saw y last time, we'll see it again. But how much bigger tells me whether I want to reject the null hypothesis. Okay, so if the difference is too large, then we would reject. So we compare the SSE of the reduced model to the SSE of the full model. If it's much bigger than 1, then we reject. But the question is how big, how much bigger, and for that we have to like understand the distribution of this. And I mentioned that this has an F distribution. This is not correct. Will not have an F. If you divide these two, this unfortunately, okay, this has a distribution that you can like figure out numerically at least, but will not have an F distribution. It's close, but it's not, because so we'll see, like if you normalize this and normalize this properly, each one would be chi-squared, but they're going to be related. They're not independent. So we want a version like something like chi-squared divided by something chi-squared, both independent. Then if you normalize by the degrees of freedom, you get an F distribution. So numerator and denominator have to be independent. These two are not going to be independent. So that's where this idea of additional extra sum of squares come in. What happens is that if I instead, so the proper way is this. Instead, I can compare this, like let's call this double tilde. This they call it F hat. This is still not F hat because it's not normalized, but let's tilde. If I do SSE, M reduced minus SSE, M divided by SSE, M. So SSEF, this is going to be always bigger. And we'll see this difference is still going to be a chi-squared. This is going to be chi-squared, and they're going to be independent. So this extra, so they call it extra sum of squares, that's independent. And if I divide this by its degrees of freedom, so we'll see what that is. And this divided by its degrees of freedom, because the numerator and the denominator are independent, which we haven't seen. Then, and then they have chi-squared, blah, 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 blah. And a chi-squared distributions in each has chi-square distribution, then we get that F tilde, FR. This is not going to be F hat for me. We'll have an F distribution. So this motivates us to look at this different. Okay. Again, might be not quite clear why this is, but by the end of this course, hopefully you like understand everything that I wrote here. So why they're independent, why each one is chi-squared. But working with this is not that different from the original one, because if you look at this, this is just this divided by this minus 1. Okay, so instead of comparing it to 1, we're going to compare it to basically 0. So if SSE, so if this is very close to that, then this is going to be close to 0. And so the top one is actually not centered because it's centered around 1. But not centered. Under null will be very close to 1. This is under null will be very close to 0. Sounds good? Questions? Okay, so this brings us back to this nice geometric picture. So let's see what these guys are. So full model, y is equal to x beta plus epsilon. And then for geometric interpretation, we're going to look at the mean of the y vector, which we call mu. So mu is in the image of x, which your book writes as L of x, and that would be this subspace here. In this case, it would be the plane. The reduced model, I plug in the constraint version, which is beta equals z gamma. I get a new design matrix. I get a new basically regression. This design matrix has an image, the image of xz, and this image of xz will be inside the image of x, which is very easy to show as an exercise. So in that case, this was our representation of image of xz, which you bookrise LA of x. So it's like L of x constrained by those A, which is not a good notation necessarily. And and then what? So you can identify these SOCs. So SOC of M would be the residual sum of squares. And this is like sum of the squares of errors. So SOC, sum of the squares of error. Some people call it residual sum of squares, RSS. Your book calls it SOC. Norm E squared is the SSE of model M. So that would be projecting Y onto this plane. You get mu hat. And the residual vector is E. You can see it, and it's orthogonal to the entire image. The second model, I'm going to project Y onto this its own subspace, which is image of XC. So I get what we call mu hat A. Again, not necessarily a good notation. A is that A matrix, yes.
And that would be also XZ gamma, right?
It wouldn't be XZ gamma. So close. So what is mu hat A?
After you model, it's
The fitted value. So XZ gamma is not the fitted value. It's like the actual mean. So there is a true mean vector. Yes, great. So that would be exactly. So mu A would be XZ gamma, which we are not showing in this plot. Mu hat A would be XZ gamma hat. Okay. And then EA would be just Y minus mu hat A. And you can see it from the plot. Y minus mu hat A. It's that E, and it's that like this guy. This is E of A. And then you recognize, so there's a lot of orthogonality. So E of A is orthogonal to mu hat A and to its entire image. Okay. So E of A is orthogonal to that line. Like geometrically look at the E of A, this is orthogonal to this line because you're projecting onto that line. And in particular, it's orthogonal to mu hat A. I'm also projecting Y down onto the image of X. So E is orthogonal to the entire image. So this E is orthogonal to the entire image. So it's in particular orthogonal to mu hat, but it's also orthogonal to mu hat A. Okay, so there's a lot of stuff here, so I write it here. So E is orthogonal to the image of X. So we know that this relation holds, so E is going to be orthogonal to image of XZ as well, because everything that's in XZ is in the image of X. So you can see that this E is orthogonal to everything on the line, because the line is in the plane, right? You also know that E of A is orthogonal to the image of XZ. Okay. Now, that's not necessarily relevant. I'm going to remove that. So this one I need. So from this, I get that E is orthogonal to mu hat A. Why is that? Because mu hat A is in the image of XZ. I also know that E is orthogonal to the image of X. So from this, I get that E is orthogonal to mu hat. Why? Why is that? Mu hat is in the image of X. You already know that. So from these, I get that E is orthogonal to mu hat minus mu hat A. This is easy calculation. Okay. Write down orthogonality is just E is orthogonal. So you can write E transpose mu hat A minus mu hat is E transpose mu hat. A minus E transpose mu hat, both are 0. Right, so this is inner product. So that proves that E is orthogonal to mu hat minus mu hat A. And we also know that if I calculate mu hat minus mu hat A, right, plus E, so this is one important fact, fact number 1. Fact number 2 is that if I calculate mu hat minus mu hat A plus E, so what is E? E is y minus mu hat A, sorry, y minus mu hat, right? So this difference, mu hat minus mu hat A plus E, so E is y minus mu hat, what would I get? Sorry? Which is, what is y minus mu hat A? Sorry? EA. EA, yeah. So this is like the residual vector in the reduced form. So we prove this nice identity that the 2 tells us that mu hat A, yeah, let me write it the other way. So EA, which is the other side, is equal to mu hat minus mu hat A plus E. Okay, so I have this fact. And from fact A, we know that these two components, so mu hat minus mu hat A and E are orthogonal, and they sum to EA, so we have the Pythagorean theorem. We can already see it here. So mu hat minus mu hat A plus E gives me EA, and they're orthogonal these two sides. So from like 1 and 2 implies that EA squared is equal to, you can expand. So if you want to square this, algebraically expand, you get this squared, norm this squared plus norm that is squared plus twice the inner product. But the inner product is 0. So you get just mu hat minus mu hat A plus E squared plus twice the inner product, which goes away. So we have this identity, which is the key identity. Okay. So this side is the SSE of M reduced. This is the SSE of M full. This is the reduced model. This is the SSE of the full model, and this part is positive, not negative. Okay, squared. So it shows that the SSE of the reduced model is always bigger. And exactly how much bigger is that mu hat minus mu hat A squared norm? So the difference which we want, which turns out to be independent of SSE of M, is exactly this quantity. So sometimes your book writes it as like that. I usually write it as the difference of the SSEs. But in any case, this difference is what matters to us. Okay. Sounds good? Yes.
So that part is you have minus you had A.
Yeah, great. Hat, everything hat. So these are all quantities that you can evaluate. So this identity you can verify in practice. So you fit the model, the full model, the reduced model, you calculate the residuals, you calculate the fitted values, this identity has to hold. Otherwise, something is wrong. Sounds good? So now anyone remembers what like the meaning of the SSE was? Or so this is called sometimes like the geometric version of the decomposition of the variance. So if you imagine, like think of the sum of squares as measuring variation, how big the errors are. Okay. So this is saying one particular variation is decomposed into 2 pieces. Okay. So this SSE is decomposed into that part, which sometimes this is not a standard notation, and we can write it as extra sum of squares or additional sum of squares, which doesn't have a good acronym, so I'm not going to write it. extra sum of squares. So SSE is extra sum of squares plus SSE. And additional sum of squares or extra sum of squares. So what are the interpretations, if you remember? The same quantity here. SSE model reduced extra sum of squares. This is SSE. So what is the interpretation? Statistical interpretation. So what is the statistical interpretation of the SSE? So if you understand this picture, so everything becomes clear. So image of X is like the directions or variations that the model can explain. So anything in that image is explained by the model. Anything outside cannot be explained. So the orthogonal directions cannot be explained. So Y, as you can see, so if there was no noise, okay, so Y is mu, the true mu plus epsilon. So the true mu, as you can see, mu plus epsilon. Mu is in the image. So that mu is in the image. So if there was no noise, Y would be in the image and everything would be explained by the linear model. Because of that extra noise, the epsilon Y is outside. So that noise has a component which is in the image that can be explained. But the part, so when you fit the model, you fit like you get mu hat. Okay, this is as close as you can get to Y. So this part of the variation in Y you can explain by the model. The part that remains is E. So E is orthogonal, so E cannot be explained. So you can think of the SSE, which is the squared, this guy, as the variation that cannot be explained by the regression model. Okay, so SSE is the variation that cannot be explained by the regression model. SSE reduced, this is also the variation that cannot be explained but by the smaller model. Okay, and you can see because it's smaller, the variation of the part of Y that you can't explain is bigger. Okay, this is smaller because you like the space is bigger, you can explain more. The other one is smaller, so the image is smaller, so the error is bigger. So the unexplained is like the residual. Let's not call it error. The residual, the part that you can't explain, is bigger. Okay, so this is saying that the unexplained part of Y that's not explained by the reduced model can be decomposed into two pieces. One part, this part, that is further explained by the bigger model. So this part of the variation you can see, so I can decompose this part. This is the unexplained variation in Y. By the reduced model, I can decompose it into a part which is in the full model. So the model picks this, the full model picks this part, explains this part of the EA. So what remains is this part, which is A. Okay, so you fit the reduced model, you basically project Y onto the reduced model, you explain some of it, but what remains is this EA. Now, part of that EA I can further explain by the full model because full model is bigger, there it picks up more direction. So this one, this direction of EA I can pick up by the full model. What remains is what the full model cannot explain anymore as well. Okay, so unexplained variation by the reduced model can be decomposed into a part that is explained by the full model over the reduced model, plus a part that's not even explained by the full model. Okay, and how big this part is tell you how good the full model is over the reduced model. If this is very small, it doesn't, like, the full model cannot explain much beyond what we already have. If this is small. If this is very big, I pick a big chunk of the unexplained variation, explain it, and then I reduce the unexplained part very much. So that is, let's say, linear models in one picture. The F-test, the entire sort of classical regression in sort of a nice little picture, right? So this is the kind of like picture that's worth 1,000 words. So you can like write an entire like regression book if you understand what is going on here. And you can write a linear algebra book on the side. It's like linear algebra / statistics. It's a very nice application. So you can translate from statistics to linear algebra back. Fitting a model is like projection. Explaining the variance. So variance would be like this norm squared of the errors. Not variance, but it's just a variation. So nested or submodel relation is just being a subspace. Okay, so models in this case are subspaces. So models, like in linear models, models are linear algebra subspaces. Fitting the model is projecting onto the subspace. Residual is just unexplained variation, let's say. And so the Pythagorean theorem basically is the decomposition of the variance. Okay. The statisticians call it decomposition of the variance. Traditional mathematicians call it Pythagorean theorem. Sounds good? This you have to look at, like go sit in a quiet place and look at this picture and try to contemplate all the relations. It takes a while, but once like it clicks, then everything becomes clear. Questions, comments? So if you understand this, you'd understand what happens if there's no noise. Okay, so if there's no noise, can you tell me what each of these quantities would look like? So if there's no noise, y would be equal to mu, and so y would be in the image. So y would, well, in that case, what would be mu hat? What would be mu hat A? What would be E? Yes.
Mu hat and y would be the same.
Great.
And then when you do the reduced model,
So what would E be then?
0.
E would be 0. So basically what would happen in that case is that this would be y. E would be 0, so y drops down. When I do the reduced model, what would happen?
Reduced model mu hat A, still mu hat A, that doesn't change. But then EA would also be the same as mu hat A.
Okay, so this would be reduced. So this would go down basically all the way. So EA would be equal to that. The other one is still the same. So basically this like the part that out of the plane is going to go out, and some of these collapse to each other. So EA collapses to that, Y collapses to mu hat, E collapses to 0. This is great, but this is one situation. This is the situation where, so mu is, this is always true, by the way, but this is where mu is in the image of X, but not on the smaller space. Okay. It could be that, so the noise is 0, so mu is in the image, but it could also further be on this smaller model, because this is also in the image. Right? In the case where mu is on the smaller model, what would happen? So suppose that when I reduce y, so this is going to be my mu. Then everything collapses to each other. So this mu hat would be the same as this, and this dimension also goes away. So under the reduced model, y is equal to mu hat is equal to mu hat A. All the errors are 0, so everything is like on top of each other. So that's basically this picture. So if y is equal to mu on this LA of X, mu would be equal to mu hat is equal to mu hat A, and E and EA are going to be 0 if the noise is not there, but mu is not on the smaller subspace, but on the bigger subspace. Then I would have a genuine. So mu would be equal to mu hat. Y is equal to what mu is equal to mu hat, but when you project it, you get a different thing. Okay, that's the one that Rishi mentioned earlier. So you collapse one half of like the top part, but there is this triangle here. So there's a genuine component here. But if the mu is originally on the image of XZ, so the other situation happens. So everything would collapse to each other, and EA and EA. So both would be 0. So you can see based on this projection, I can tell which one is which. So if there is no noise, if I project, so if everything collapses to each other, like, and then all the errors are zero, or like residual is zero, I'm in this situation. But if I'm under the alternative, there's going to be a component here. So I can tell whether the full model is going on or the null model is going on. So that tells you that this test is going to work. So the noisy version is just a noisy version of this. Okay, so if you have a noise, so you have like this bigger picture, but you perturb both of these a little bit. So nothing will be the same as each other, but in that case, so y would be a perturbation of mu, and then both of them would be perturbations of mu. In this case, there's going to be a genuine component which you can explain. So once you understand what is going on, you can do the noiseless case and verify that this test that you're doing, basically comparing these two, is reasonable. Because even in the noiseless case, if the null is true, then all of these would be zero. If the null is not true, then this is going to be non-zero, and I can tell the difference of these would be non-zero. So the difference of the errors under the null and under the alternative is different, even if there's no noise, because of this extra component, because of this triangle basically here. Okay. In any case, so this is like another way of seeing that this test is useful. Okay, just for go like sit in a quiet place and think about what happens if there is no noise under the null and under the alternative. Under the null, we have more information about mu. Mu is actually in the image of xz. Under the alternative, we just know that mu is in the image of x, but maybe not in the image of xz. So in the bigger space, but not on the smaller space. So questions? Okay. So here's the kind of result that we eventually prove. The idea is that this, I want to do this test. So EA squared is equal to mu hat minus mu hat A squared plus E squared. The idea is that if I divide these by sigma squared, right, I have this identity. So we already know, we haven't proven, but I know the distribution of this guy. Right, that's the residual sum of squares divided by sigma squared, right? What is the distribution of this guy? Chi squared with who's talking? Yeah. N minus p plus 1, d is p plus 1. So we'll see that later. This one is also going to be like that, because this is also a sum of squares in a particular regression. So we're doing a regression in a reduced model, still a regression. So this is going to have a chi squared. Anyone knows the number of degrees of freedom? So EA is the residual in y equal xz gamma plus epsilon. So this is n by, if you recall, d minus q. So we had originally d degrees of freedom, d parameters. We lost q of it due to the constraint. So this is going to be q by 1. So in that case, what would happen? What is the degrees of freedom of this q? No. So m reduced, m full is y x beta plus epsilon. So this is n by d. This is d by 1. And the residual sum of squares has degrees of freedom n minus d. So now, how about the other one? N minus d. Yeah, minus q. I'm going to write it like that. Yeah, or like n minus d plus q, or n minus in parentheses d minus q, because that's the like the number free parameters. And this is going to be true if this is full rank. And it's going to be full rank if x is full rank and z is also full rank, which is like true if the constraints are linearly independent and so on. So we know these two. The point is, there's this theorem that we'll see later. Anyone knows the name of the theorem that I want to talk about? So you have this identity. It turns out that each one of them is a quadratic form. So these are quadratic forms. We'll see what they are. So I have 3 quadratic forms. And one I can write as the sum of 2 other quadratic forms. I know that this has a chi-square distribution. I know that this has a chi-square distribution. There's a theorem that tells me this remaining part has to have a chi-square distribution as well. And moreover, the 2 components have to be independent. So that's a theorem in classical statistics. Anyone knows the name? It's called Cochrane's theorem. We'll see. Cochrane. Yeah, now I forgot how to write. Cochrane, something like that. A or O, I forgot. We'll see. But it's called Cochrane's theorem. If you have 3 quadratic forms, which you don't yet know what they are, but these are quadratic forms. And if I can write one as a sum of 2 other ones, and the bigger one, the one that can be decomposed, has a chi-square distribution. I know that. I know this. I haven't proven, but we'll prove that in a regression, usual regression, the residual, if you divide by sigma squared, it will have a chi-square. The residual sum squares divided by sigma squared will have a chi-square distribution. So I know these 2 from that fact, and I have this identity. Then Cochrane's theorem tells me the remaining part has to have a chi-square distribution. And you can imagine what the degrees of freedom would be. Anyone knows what the degrees of freedom, like, can guess? Say? It should be Q. So it will be the difference of these 2. So the degrees of freedom should add up. So if you look at it would be like n minus d minus q minus n minus d, which turns out to be, if you do the calculation, just q. So q, if you add it to this, you can see. If I add q to this, I get back that. So the difference of the degrees of freedom. And furthermore, the 2 components are independent. So that's the content of this theorem. So mu hat is the projection of y onto the L of x, or the image of x. Mu hat A is the projection of y onto the, this is for us image of x. This is image of xz in our notation now. And then this difference divided by sigma squared is going to have chi-square distribution, and this guy and e squared are going to be independent. So this is a result from Cochrane's theorem. The fact about quadratic forms, we prove once we talk about that. Okay, yes.
Above this, where you wrote that, was that on the right? Suppose, so when you have the full model, we say beta, but on the reduced model, we use gamma.
That's what we usually, yeah, that's how I'm going to the notation. And the full model, I have beta as a free parameter, and the reduced model, I have gamma. Yes, and the relation is beta is equal to, so this model transforms to this if I impose this restriction that beta is z gamma. Okay, so this is the bunch of constraints and elements of beta, because z is d by d minus q, and we're assuming d minus q is smaller, so it puts some constraints. Okay, so this one will prove actually we're not going to prove the Cochrane's theorem, but I'm going to tell you what Cochrane's theorem is once we know about quadratic forms. And you're welcome to try to prove it. It's a very nice theorem. It's not easy to prove. It's like tricky to prove, but somewhat doable if you have time. It's a very nice result that if you can write a quadratic form as a decomposition of 2 quadratic forms, and you know that this side and one of the other sides are chi-squared, then the rest has to have a chi-squared distribution. And the two components have to be statistically independent. So independent like statistically, which is a very strong result statistically. So these are random variables, if you remember. They're all like in the abstract sense, if you recall. So again, there are two different views. In practice, they're numbers that you calculate. In our abstract view, they're all random variables because they all derive the randomness from the epsilon. Or y is random, epsilon is random. So they are random variables, so they have certain distributions. The distribution of this would be chi-squared. The distribution of this would be chi-squared q. The distribution would be chi-squared n minus d. And they're going to be they're going to be what? The two components will be independent. Okay, so if you know this fact, so any questions about this? If you know this fact, and you know what an F distribution is, now I can construct an F distribution. So what is this definition of an F distribution? How do you get an F distribution? Yes.
You divide two normalized chi-squared.
Two normalized. So normalized means yes. So if I have let me see if I have any. Yeah, so if I have U1 and U2, and U1 is chi-squared with D1 degrees of freedom, and this is chi-squared with D2 degrees of freedom, and I know that U1 is independent of U2. This is very important. Then X, which is like U1 divided by D1, then divide by U2 divided by D2, we'll have an F distribution with degrees of freedom, which is D1, D2. So F has two parameters, 2 degrees of freedom, D1 and D2. Okay, so if that's the case, if you go back up here, from this fact, I get that if I look at, so these two are independent. Okay, so if I divide mu hat minus mu hat A squared divided by Q, and then divide it by E squared, divided by sigma. So this divided by sigma squared, and then further divided by Q. Okay, that's in the numerator. This is funny. So I'm going to write it like that. Divided by sigma squared, this is chi squared, and then divided by Q. And then I have E squared divided by sigma squared. Now this is a chi squared with n minus d degrees of freedom, and then divided by its degrees of freedom. Okay, so this turns out to have an F distribution with Q and n minus d degrees of freedom. But this simplifies because if you do the calculation, the sigmas would cancel out. These sigmas that are unknown go away. So this is really a nice quantity that I can calculate. It's a pivot. And it's actually not a pivot, it's like a statistic at this point. Not pivot. Divided by n minus d. So that would be my statistic, which I call f hat. So this is the statistic that I can calculate. In practice, the extra sum of squares divided by its degrees of freedom. Further, divided by the SSE of the full model divided by degrees of freedom. That would give me a statistic, which, all of this falls under the null. So I should have said that. So these distributions, these hold under H naught. So this is true under the null. So this theorem assumes that we are under the null. Assume that the null hypothesis is true. Okay, the null hypothesis true means that beta is actually Z gamma. Because I could have like a true model in which beta does not satisfy these relations. Then this would be large. But if I'm under the null, this would be small. And then how small is characterized by the F. So we can determine what we care about usually is the distribution under the null, at least in classical statistics, because then you can set the level, the threshold, the size of the significance level, p-values, etc. So under the null, this quantity will have an F-distribution because the two pieces are, again, independent, and each one has a chi-square distribution. And this follows from the decomposition that we actually proved by geometric ideas, and the Cochrane's theorem, which we haven't seen or proven, but hopefully, like I repeated multiple times, you understand, like remember better. Okay. So this is a very general result, and the proof wasn't difficult, except for the Cochrane's part. Follows from the geometry, and it has a lot of intuition while we do this geometrically, and as it happens, it's very nicely, like has a nice distribution that doesn't depend on anything other than the degrees of freedom. So I can actually calculate this in practice, compare it with the tails of the F distribution, and decide whether I'm like too far off or not. So this will have an F distribution is not centered around 0 because it's the distribution of a non-negative quantity. So everything here is not negative. So it would be like something like that. There's a peak. And I'm going to compare it to the I have an estimate of what the mean of this is. Even the mean is funny. So the mean of an F distribution. It's not so obvious. But we'll have it like a slide later. So the mean is going to be. Anyone knows what the mean of an F? Yeah.
If it's that one with n minus d, n minus d over n minus 2.
Here. So the expectation would be
The second degree of freedom over the second degree of freedom minus 2.
the second degrees of.
I mean, it's like, I don't know how to, it's like n minus d. It's like
N minus d, where n minus d should be?
what?
Numerator or denominator?
N minus d is in the numerator. I think, I thought. And then in the denominator, you also had n minus 2.
Oh, there's no q here, you're saying. So let's check. That's great. How do we check? So this was good. And you can see this converges to 1 as n goes to infinity. So the sample size. So it's going to be like for large sample size relative to d, this would be around 1. And then you can check how big you are, like, and the variance is about like, if I haven't done it wrong, the variance is like, the variance of f hat is about, asymptotically, like 2 over n minus d. We'll see that later.
Isn't that one q?
D2, it was D.
That all the d2's canceled off, and only have the d1.
Good question. Why can I do both? So if you let d2 go to infinity, so d1 plus d2 minus 2 is about d2. And so you get d2 to the 3. So 2 times d2 to the 3. Here it would be like, oh yeah, right. So d1 times d2 to the 3. So you get 2 over d1. Okay, yes, you're right. Good, because that would be bad. So 2 over d1, right? Yeah, so this would be like d2 to the 3. This would be d2 to the 3, so I get 2 over d1. Great. Yes, that wasn't quite correct. So let's go back. So asymptotically, so this is not exact, but asymptotically would be like 2 over q. So if q, for example, is quite large, the number of constraints, this would be smaller. And so it's like roughly this plus minus 2 over q is like your rough guess of whether you want to reject. If, like, for example, let's say q is 3, like maybe twice. 1 plus 2 is not necessarily good, but let's say 1 plus minus 2 times the standard deviation is a rough measure. So if under the null, we can calculate better. So basically, you can calculate what this number should be. That's not necessarily 2, but quantiles of f basically. So let's do like maybe not 2. Like let's say I'm going to do phi, the standard deviation away anyway. Because sometimes So you can get a sense. Let's say if Q is like 4, okay, so 2 over 4, like root 2, 5 over root 2, it's not that big. 5 over root 2, maybe 3. It's like 1 plus minus 3. So if you get like a value which is like 40, this is very much in the tail. Okay, so you reject. You even have like the F, this like proper F quantile. So you have to compare to the quantiles, but this was a rough calculation to get a sense. Yes.
Get 5 from?
Just out of the like my pocket. Yeah, like 2 standard deviation, 3 standard, 5 standard deviation is too large, so it's like very unlikely. But you can look at the tables of F distribution, see how it doesn't tell you about the standard. It just tells you like exactly what this, how far you have to go away. It doesn't tell you about the mean. So what you really need is so what you'll do is like look at the tails. So this would be, what would be the quantile? So the quantile would tell you exactly where you are. So if I look at the, it's hard to write, but let's say F, U, and N minus D, 1 minus alpha. This is the alpha quantile. So this tells you the location here such that this mass is 1 minus alpha. So then this part would be alpha. So the proper way of doing it is look at an F table, look at the 1 minus alpha quantile. That location is where alpha of the mass is above. So that's where you want to put your threshold. So if you're above this, so you want to reject, right? So you want to reject when you're above this value. And if you reject when you're above this value, alpha percent of the time under the null, you're going to reject, which is good for you. Okay, so that's how you do. Proper. The top is like rough calculation. You can do 2 standard deviation, 3 standard. So it's heavy tailed. So let's say 5 standard deviation. It's very unlikely that you're 5 standard deviation away from the mean. And if you end up with like a statistic which is like 100, the value is 100. It's big, but big relative to what? Like the relative to the. So these are asymptotic calculations. N is big, N might not be big. So the proper way is doing this. But if N is very big compared to D, and then you have a good like estimate like that. It's like rough. This is like back of the envelope calculation. These two. This. Back of the envelope. This is like the proper way. Proper way. Okay, and this is the proof. I will come back to it. The proof is like basically Cochrane's theorem. You can see. And then we have talked about this. This is our D. This should be N minus. Yeah, N minus D, which is P plus 1 usually, but doesn't have to be. Alternative notations. Yeah, your book writes EA squared as S beta hat A, S beta hat. That thing is called additional or extra solid squares. We had seen this identity, degrees of freedom. Okay, the number of restrictions over the full model. So the number of restrictions is basically Q. So that's fine. You can perform a test if you have, you can perform the test if you have that, or we have the reduced solid square. So if you go back up, the way I usually like to do this is, okay, let me maybe take this out. Right. Take this out as well. This goes here. Let's take this out. Oh. Okay, now this is nice actually. So this is back of the envelope calculation, right? And this is the proper way. Proper way using the quantiles of F. Okay, there's another way to write this, which is what I have been doing so far. So this guy, so remember we have EA squared mu hat minus mu hat A. If you can calculate everything, it doesn't matter how you do it. So you can do the difference, you can calculate the difference to fitted values, basically. But this is SSE of M reduced, and this is the SSE of M. So we can write the F test as SSE of M reduced minus the SSE of the full model divided by Q, which is the degrees of freedom. That's the basically extra sum of squares, divided by the SSE of M divided by N minus D. So this will have under the null and F distribution with Q degrees of freedom and minus D degrees of freedom. And this would be our F statistic. This is sometimes easier to calculate if you have given SSEs, okay? If you have everything, it's up to you, yes.
That's the test statistic that then we would compare, and then we would calculate the probability minus p value.
Yes, yes. This is basically the same statistic that we talked about here. Right, it's exactly the same thing because mu hat A minus mu hat A squared. So there's just one F statistic. Okay, but this works for under the null, have an F distribution, so we can compare it to the quantiles of F and then see whether we want to reject or not. Okay. There are many like different reformulations of this. So you can write it as, for the exam, if you want to do it, if you look at this, it would be like N minus D divided by Q times, so take the coefficients out, they flip, divided, you get SSE M reduced divided by the SSE M minus 1. And there are even different versions. So play with this. We can write it in terms of the R squared and stuff. It's a very good exercise. Yes.
So D was P minus 1.
D is the number of parameters.
Plus the row column.
Depends, yeah, parameters.
Q is
Of the
max.
no full model. So D is the number of parameters the full model. Usually P plus 1, but if you don't have an intercept with you P, whatever the number of is. What is Q? Number of linearly independent constraints. Okay.
So the example at the top that was 2.
Which example?
The very first one. Like,
Right, beta 0 equal to 0, and let's say beta 1 is equal to beta 2. What would it be? 2, yes. There are 2 linearly independent constraints, so Q would be 2. It just depends on the number of constraints, not on the sample size or anything. It has to be less than D, right? Less than or equal to D. That's the maximum. Sounds good? So let's do a quick example. So we covered everything here. So here's an example, a nice example. And then you can see how powerful this general framework is. You can do many different type of tests using just this simple, not simple, but just the abstract F test. So the model is, I want to do basically this problem. So we have 5 drugs, oral contraceptives. It doesn't matter, like 5 drugs, and then we want to see the effect on the cholesterol level, HDL, good cholesterol. So you basically have a sample size of 50, and the thing is, each, like, you divide the people into, like, let's say 5 different groups, and give each group one of the drugs. And then you measure the HDL before giving them the drug and after giving them the drug. And you want to measure somehow the effect, but you want to see, like, for example, if the HDL dropped, actually it has to go up. If the HDL went much, like, what, like, before was this, and then after went very high, it's like good. If, like, if it was before, it was like something, and after it didn't change much, or maybe became like went down, it's bad. But so you can see there are 5 different groups, and for each different group, like, this difference could be different. Okay, so the drugs could have a different effect. So this we can model using, like, a nice multiple linear regression problem, where this y is the cholesterol level after, this z is cholesterol level before. This is like the baseline. Okay, this alpha measures, like, how much, like, a baseline drug affects things, and then we have these extra effects. So x1 is an indicator variable, tells you whether you took drug 1 or not. So if you took drug 1, so you have alpha z, or maybe, like, yeah, so alpha is not the effect of the drug, basically. Alpha is like what happens, like, today you have this cholesterol level, tomorrow you have that cholesterol level. There is, like, this link between them, nothing to do with the drugs. But if you have taken drug 1, then you add it by beta 1. So beta 1 just adds up to the effect. So x1 is either 0 to 1, and it's just 0 to 1 for just exactly one of the so exactly one of x1 up to x5 is 0 to 1, or 0, 1. These are indicator variables, and this way it allows you to model the effect of different drugs. So the effect of drug 1 would be like alpha. So if you took drug 1, your model would be basically this. If you took drug 2, it would be alpha z plus beta 2, and so on. So you can model all of these in a single regression, and then you can compare the betas. So for example, if you want to see whether all of the drugs have the same effect, that would be the test of, like, beta 1 is equal to beta 2 equal to beta 5. So this was a little fast. Next time I'll come back and sort of do this properly. It tells you, like, interesting, like, there's a bit of art to how to set up these problems as regression, but once you set it up as a regression, then you can do interesting various tests using just the F test that we learned. Okay, thank you, guys.